Hello, dear listeners. I'm pleased to present to you today Lucas Darlavoie, who will give us a lesson about machine learning frameworks within my YouTube channel.
Yes, thank you, Mohamed. Hello, everyone. We'll be giving you this lecture on machine learning with a specific focus on performance guarantees that can be obtained within machine learning frameworks. We are very enthusiastic about these results. Hopefully, we will share this enthusiasm with you, and hopefully, this will be useful in your endeavors within machine learning. Enjoy.
Thank you, Lucas.
Hello everyone, and welcome to this first lecture on machine learning. This video is the first of a series of other videos, which will be the English translation of a series of videos that already exists on this channel that was done by Mohamed on this topic of machine learning. Once again, this is a joint work with Bartek Blaszczyzin from INRIA and Mohamed Carré from Orange. The goal of this series of video is to show you the inner workings of machine learning, and most importantly, to show you that machine learning isn't magic, that there is actually a mathematical theory behind it, mainly rooted in statistics, that allows machine learning to stand on its 2 feet. And we will see through various frameworks in this first lecture how we can already start to have a basic theory of machine learning and have already some insights to show why machine learning works. I don't know if you've already experimented with machine learning, but sometimes it's like when it works, good for you, and if it doesn't work, well, that's too bad, but how can I try to troubleshoot? Well, basically, what we will see here is that the mathematical tools that we have allow us to have guarantees of performance. So basically, we can already say, without running a single algorithm, whether a framework will actually give us results or not. So this is very powerful. We will have guarantees of performance if we apply these results carefully on our work. So that's very interesting, very exciting. So let's try to do this together today. Basically, we will start with a quick introduction. And after that, we will see 3 frameworks. The first one is the most basic one, without any assumption that you will all be able to follow. We'll go step by step through it and apply the basic principles and define the most important concepts that we will have through this video, which are empirical loss minimization and PAC-learnability, the 2 main concepts that we will be talking about here. And these 2 other frameworks, the noisy learning framework and the general learning framework, are none other than extensions of this first basic learning framework. So yeah, this is maybe the most important one to be able to follow the rest of this lecture. But don't worry, we will move slowly. And after that, of course, as always, you will have a quick bibliography giving you the references should you be interested to check them out. So a quick introduction on the topic of machine learning, if it ever needed one. Basically, everybody is talking about machine learning today in tech because data science in general is becoming widespread in order to solve many problems more efficiently than before. This is particularly true in telecommunications, which is why we are talking to you about this. Oops. And as I was saying, data science actually has mathematical foundations, mostly stemming from statistics, that help it work. And that is why we will be talking about this today, because oftentimes we assimilate machine learning to softwares, to algorithms. And as we will see, this is very entangled. mathematics and software are very imbricated in data science, and this is particularly true in bibliographies, in like references of machine learning. But we will see here that it's interesting to treat the mathematical part and the algorithmic part separately. So today we will be talking about mathematics. And so yeah, this is what we aim to do here. And these concepts that we will be presenting actually are useful for both machine learning and deep learning. And if you wish to write codes, you may also refer to a presentation that is available in the bibliography that you will see, giving you some insight as to how to properly code and begin exploring machine learning development. But for now, we will be talking about mathematics and the whole theory behind machine learning. So as I said before, we will start with the most basic learning framework. So if you've never heard of machine learning, first of all, welcome. And we will start very slowly with what it means to learn with a machine learning algorithm. Basically, in the most elementary sense, we have observations between an input and an output. For example, let's consider that there is a black box that takes inputs and turns them into outputs. The goal of machine learning is to guess the function within the black box that maps these inputs to outputs. That's it. That's the learning part. We are trying to learn the function that maps inputs to outputs through experiments and through a learning process. And through a large number of iterations, we try to understand the mechanic behind this mapping from inputs to outputs. This is it. So basically, that's what we will try to transcribe here. As I was saying, a basic learning framework is composed of these two elements. The first one is these two spaces. So an input space and an output space. Basically, the elements we were observing through this black box. So let's call an input space the space in which we have our inputs within the black box, and the output space, what comes out of the black box. So these spaces are the set X endowed with its sigma algebra f of X. If you don't know what I'm talking about when I say sigma algebra, either go check the video on measure theory on this channel, or just forget I ever said that. Just consider this set X, which is the set of input values. And the other set, Y, endowed with f of Y, which form the output space. So once again, this is what we observe. We observe these couples of input-outputs, and we try to guess what links these inputs and outputs. So first item. And second item, when we talk about machine learning, we talk about algorithms, of course. So we can talk about algorithms, but we can also talk about learners. This is a synonym for a learning algorithm. So this is what we will use here, a learner, and we define it by the letter A for algorithm. You guessed it. So what is a learner? So a learner is a measurable mapping which observes what we've talked about, this set of input-outputs. Let's consider, for example, we have 100 items of input-output, input-output, input-output. We have 100 of them. So in that case, we have n equal to 100. So the union of all these observations of input-outputs is what we feed the algorithm. And the goal of a learning framework is to guess, the goal of this algorithm is to guess the function which maps the input to the output. For now, that's very clear. And this function, of course, is a function that goes from this set x to the set y. And so we call M the set of measurable functions that go from x to y. This is the goal of our algorithm, is to return a function from x to y, which is its best guess of telling us what links the inputs to the outputs. So yeah, an algorithm is none other than this mapping here. And once we've said that, we can talk about, in practice, what does an algorithm do? So we just said it orally before, but we can formalize it now. It takes as an input a finite sequence of these couples of observations, input, output, etc., until the size of the set that we use. And this set that we use, we can denote it S of n. We call it the training sequence. Basically, this is the set of observations that we feed to the algorithm. This is the training sequence. And the result of this algorithm, which is the function, the best guess of the algorithm linking inputs to output, is called the hypothesis. This is written h. It's a function from x to y. And this is a measurable function that is returned by the learner. So yeah, we've here explained all the intuitions that we have when we talk about machine learning. We are trying to guess a link between an input and an output as best as we can by observation, by force of observation. This force of observation is defined here as the training sequence, and the result is the hypothesis. Okay. So mathematically, we can summarize the learning framework with this equation. So we have a training sequence to which we apply the algorithm, and in return, we get an hypothesis. So this equation actually summarizes the basic learning framework. And the goal of the learner, the goal of this algorithm, is to minimize the loss of this hypothesis. Basically, what this means is that we wish to have the best hypothesis possible, the hypothesis which describes as best as possible what links an input to an output, the inner workings of the black box, if you wish. We wish to approximate that as best as possible with our hypothesis H. So this is the goal of the algorithm. And in order to model this framework even further, we can talk about two more elements that are not known to us. If they were known to us, that would be much easier, but they are not. The first one is a probability measure that we write Q over the input space. And this probability measure represents the input distribution. So basically, it tells you how the data that we have as an input is distributed. And this is not something that we have. We only observe data, and we just have them and we feed them to the algorithm, but we don't know how this data is distributed. So, but we can assume that there is a probability measure Q that gives the distribution of this data. And obviously, the second tool that we do not have, otherwise this will all be pointless. This is the measurable function f linking, going from x to y, linking the values, the input values to the output values. This is what we call the target function. This is the function that we are trying to figure out through this algorithm. And we have with this function f that all the values of y are equal to f of x for all the I. And yeah, obviously, this is what we try to approximate through our hypothesis H. And now that we have these values, input distribution and target function, Q and F, we can define the true loss. This is important to talk about true loss. We will see why in a second. But the true loss of an hypothesis, H, is defined as follows. This is a calligraphic L of Q and F for a given hypothesis. This is the probability of having an hypothesis different from the reality, from the target function. So it actually takes into account for every value of the sequence that we have, the differences between h of x and the reality f of x. And this gives you a result that we call the loss of the hypothesis. And of course, we consider that x is distributed according to Q. So this is a true loss, and we do not have access to this value, of course, because we don't have access to f, so we can't compute this. However, what we can compute, since we do not have the true loss, is the empirical loss. Basically, we have our hypothesis, H, and we have a training sequence, Sn. And we can observe that when we apply the hypothesis to the input, we have a result. And if this result is equal to the output, to y, then it means that the hypothesis is correct. And if this is not the case, we know that there was a mistake in the hypothesis. There is a loss that appears within the hypothesis. So we basically take the indicator function for the difference of h of xi and yi. And we add 1 every time we have a mistake, basically every time we have a difference between the observed output and h of xi. And we take the average of this, and we get a score, which is the empirical loss, since we do not have the true loss. But we can approximate this true loss through this average over here. And it gives us some loss for our hypothesis. And it tells us whether this hypothesis is good or not compared to others. So this is something that we can do. So having said that, we can consider the training sequence that we had before, S of n, which was the collection of the x1, y1, etc. to xn, yn. We can view this sequence as a sequence big S of n. We're talking about the same sequence. We're just seeing it differently. Big S of n of the big S, x1, big y1, etc. to xn, yn, where the x1 to xn are IID random variables distributed according to Q, which is what we saw before, and where we have that the yi are equal to f of xi, f being the target function, of course, what we saw before. So basically, we just include these unknowns, Q and F. I recall that we don't have these values, of course. And basically, this is the sequence that we have. A sequence linking random IID variables to each other through this function f. And this is denoted as S of n distributed according to Q and F. And this is for n samples. So when we have that, we can denote that the true loss, according to Q and F, of a learner is written as the comparison between the outcome, the hypothesis, the outcome of the learner applied to the sequence, compared to the reality, to f of x. And we compute the loss like this. And this is, of course, knowing a training sequence, big S of n. So yeah, this is H, this big A of Sn, this is H of x, different from f of x. This is none other than what we said before here. Okay, and last thing, we can assume, so we were talking about functions, we were talking about hypotheses within the space M, which was none other than x to y. We can now assume that there is a smaller class, which we will call the hypothesis class, H within M, which is known to the learner, and that we can work on instead of working on M. More on that in a second. Basically, this class, this hypothesis class H, represents the prior knowledge that we have on our learning framework. So if you don't know anything about your framework, this is okay. If there is no prior knowledge, we will just consider that H is equal to M. So don't worry about it if you don't know anything about your framework. But if you know that there is no need to scout all the functions in the world, and that your function looks like something within a given class, you know that you are looking for a function within a certain class. So in other words, in mathematical words, if you know that this target function that you're trying to estimate is Q almost everywhere, this is once again a measure notation, is Q almost everywhere equal to a function in your class H, that, for example, that F belongs to your class H, you don't have to look within M. You can just look within H. Fairly simple. And in another case, if you know that you have like hypothesis and you want to benchmark hypothesis, and you wish to find which hypothesis is the best, and you've seen that people have already done have supposed things to have certain hypotheses, you wish to try a certain class of functions, you can reduce the scope of your problem, and instead of searching within M, you can search within this class H. That for instance, if you found solutions on the internet to your problem within this class H, you don't have to search within M, you can just search within H. So yeah, there are reasons for people to not directly go within M, but to reduce the scope of that problem. Okay, a few results that we can have. Once again, if we take a sequence distributed according to Q and F, then we can know that for any hypothesis, we have this very useful first result. If we take a number of samples which tends to infinity, so a number of samples that is really, really big, we have almost surely that the empirical loss tends to the true loss of the hypothesis. So you are incited to take a large amount of samples. This is intuitively something that we have through the law of large numbers, which basically tells you that if you take a large enough sample, your empirical loss tends to the true loss. And in another sense, which is maybe less helpful, but still, if the true loss, if you somehow have access to the true loss of your hypothesis, if the true loss is 0, basically your hypothesis is equal to the target function, then you have that your empirical loss is equal to 0, almost surely. Of course, the opposite is not true. That would be too simple. But yeah, keep that in mind, because it tells you that intuitively you need a large amount of samples. And this is an idea that we will further on later. Last word on this hypothesis class H. Basically coming back to the first point that we were talking about here. Basically, if you know that your function f is within a class H, you don't have to search for all m. And in that case, if you know that there exists an hypothesis such that Q almost everywhere your hypothesis is equal to your function f within the hypothesis class H, you say that this hypothesis class is realizable. So yeah, the first case here, in which we know that f belongs to H, we say that H is realizable with respect to Q and F. This is just semantics, but yeah, when we talk about a realizable class, it means that we can reduce the scope. H belongs to F, sorry, belongs to H and not N. Okay. So yeah, obviously the main goal of machine learning is to minimize the true loss of our hypothesis. This is the goal. But as we've seen before, we do not have access to the true losses since we do not know Q and we do not know F. So it's difficult to, in practice, minimize something that you do not know. So what do? We use, once again, the empirical loss. And the goal will be to minimize this empirical loss. And that's why we define the well-named empirical loss minimization, which is an algorithm. So the ELM, empirical loss minimization, with respect to H, is a learner, so it's an algorithm, denoted ELM of H, that verifies this. Basically, the output of ELM of H, so this is what we describe as this, ELM of H applied to a training sequence. So the hypothesis coming from ELM of H belongs to the set of hypotheses which minimize the empirical loss for the hypothesis. So basically, the hypothesis coming from the ELM minimizes the empirical loss. And provided, of course, that it's possible to minimize this loss. And yeah, basically, this is an optimal algorithm. And yeah, if the mapping exists, so yeah, if you have a mapping from a sequence to ELM of H of that sequence, if that is measurable, we shall say that the algorithm ELM of H is well-defined. So if this is measurable, we have a well-defined algorithm. But yeah, keep in mind that ELM of H is the optimal algorithm which minimizes the empirical loss. Another word on that is the case where we have a finite hypothesis class, H. So for now, we've just said that we have a reduced class within M. Once again, we can have H equal to M, but let's say H is included within M. And let's say that this class is finite. So we consider that this class is realizable. What we said before, realizable means that the target function is within that class. It's realizable with respect to Q and F, such that an ELM of H is well defined. So let's take delta within 0, 1, and epsilon within R plus star, and n within n, such that we have this. So n is bigger than log of the cardinality of H divided by delta divided by epsilon. Basically, what this means is that we have a number of samples that is sufficiently big. So we have a number of samples n bigger than this quantity. And if this is verified, and we have a training sequence following what we said before, S of n distributed according to Q and F, then we have this first very interesting result, which is a guarantee of performance of ELM of H, basically telling us that the probability of having a loss, or a true loss of ELM of H smaller than epsilon is bigger than 1 minus delta. So this is very strong because this result is independent from Q and F. So we're able to have guarantees of performance on this algorithm, ELM of H, without even knowing Q and F. The only thing we need is that this sequence is distributed according to Q and F, but basically this is what we've defined our framework to be working in. And the only condition is that we have a number of samples sufficiently big, basically bigger than log of cardinality of H divided by delta divided by epsilon. If we verify that condition, we have a guarantee of performance on that algorithm that do not depend on any unknown variables. This is very, very strong. So it's actually beautiful to see that we have such a strong result when we have a finite hypothesis class. Once again, this is not every time, but we will see that this is also true when the hypothesis class is not finite, but we'll see that later in another video because it requires some other mathematical knowledge that we haven't talked about yet. But yeah, this is the first result, big result from this lecture. And to finish on that, and to echo what we just said before, when we have a number of samples sufficiently big, we have a guarantee of performance. And this is called PAC-learnability. So basically, we consider that a class H is PAC-learnable, PAC meaning probably approximately correct. So this class H is PAC-learnable if there is a learner A and a function NH, that's called sample complexity, that verifies that whatever the epsilon we choose, whatever the delta we choose, for every distribution Q over the input set X, and for every target function F, because this is independent from Q and F, this is a strong result, as long as H is realizable with respect to Q and F, as long as we have, of course, this training sequence Sn distributed according to Qf of n. This is a long definition, but bear with me. And most importantly, as long as we have n bigger than a certain nh of epsilon and delta, as long as we have n sufficiently big, then there is a guarantee on the performance of our algorithm. Basically, the true loss of the algorithm applied to the sequence is smaller than epsilon with a probability bigger than 1 minus delta. So this is very strong once again. As long as we have a sufficiently large amount of samples, we have guarantee of performance. And in that case, we talk about a class that is PAC-learnable, probably approximately correct. So yeah, that's it. Two important results telling you that you are guaranteed that your algorithm is going to work. This is actually crazy. You may think that I don't know, machine learning is something magical, and sometimes it works, sometimes it doesn't, and if it doesn't, well, tough luck. No, mathematics tells you that there is a way of knowing whether it's going to work or not without even starting a single line of code. So this is very, very strong. We have two big results, and they stem from, in one case, finitude of the class of hypothesis, and in the other one, it's PAC-learnability. So basically this, we have a sufficiently large amount of samples. Okay, and just one final word on this concept of PAC-learnability. Maybe it's stating the obvious because it's a corollary of what we've said before, but still a useful result. If you work in a finite hypothesis class with a well-defined ELM of H, by default, you have PAC-learnability and you know the sample complexity. It's none other than what we saw before in the theorem, but basically you have this quantity NH for epsilon and delta, which is your sample complexity, and you have PAC-learnability in any finite hypothesis class framework that you're working within. So yeah, very useful results. And once again, infinite hypothesis classes may also be PAC-learnable, but that's a story for another day. We'll talk about this in another video, as I told you. And that's it, basically, for this basic learning framework. The following sections of this video will be noisy learning framework and general learning framework. And basically, if you've understood so far what we've said in this basic learning framework, you will be good to go, because the noisy learning framework just adds the noise to this basic framework. So we will go through the same construction just with an extra variable. Obviously, we'll have a few other notions that we will introduce, but the main structure won't change. And once again, for the general learning framework, this will just be an encompassing of both the basic learning framework and the noisy learning framework. So we will just be generalizing both the first sections. So yeah, if you've been able to follow this so far, you will be good till the end of the video. Okay, so yeah, that's it for this first part, and we can now move on to the second part, which is the noisy learning framework. Okay, so if you've been with me so far, this next part is just going to be an extension of the basic case, to which we've added a random noisy component. So basically, we're talking now about a noisy learning framework, and we will see what it means right now. So basically, we've said so far that we had a black box, which was mapping an input to an output via some random function f that we're trying to figure out. But in reality, it's not that simple. It's not just a simple function that we are trying to approximate because we have noise. So we have randomness, and it's a bit more difficult. So in practice, we can simulate this idea via two main ideas. The first one is maybe the most intuitive one. It's the idea of having an additive noise communication channel. So maybe you've seen this already. Basically, you just consider an input, which is X, and a received signal, an output, which is capital Y. And you have, once again, a function linking your input to your output. But now you add a random component, which is a random variable that we have, which is W here, that we call the noise. Your signal is noisy between your emitter and your receiver. So in that case, yeah, it's not that simple as figuring out a function. You also have to take into account this random counterpart, which is the noise. Another way to see this problem is to consider the link between the input and the output, not as a function, but as a probability kernel. So if you've never heard of that principle of probability kernel, it's basically this. You're actually trying to figure out the probability of observing a certain output Y given an input X on a certain subset of your set Y. For example, just to explain to you why we have dy here, just consider that we are trying to figure out the probability of having an output Y on a certain subset of that set Y here. Let's call it B, for example, knowing the input X that we have. And the reason why we denote it kappa of dy knowing X is linked to measure theory. It's because this is a measure, and we denote measures as the following. But this basically says that it's a probability measure on a certain measurable subset of this set Y. But don't worry, we just denote it basically kappa of dy knowing X. And the main idea is just that this is the link between the input X and the output Y. Okay. And yeah, as we said before, this will be the new characterization of the link between input and output. And we do not talk anymore about a target function f, but now we talk about a probability kernel kappa. That's the main difference in this big part of this presentation between the first and the second one. And yeah, basically, the output is a random variable y with this conditional probability distribution p of dy knowing x, which is this kappa of dy knowing x. So what does this change? Not too much, actually. We have the same elements as we had before, except obviously the changes that apply to the target function. Since we do not have the target function anymore, we have the probability kernel now. So everywhere we had f is now changed. So for example, if we take the training sequence that we had before, that was called SN, we have these pairs of input-output until xn, yn. And here we do not have anymore that y is equal to f of x. We have that the y1s to yn are sampled according to a certain product distribution of the individual kappa of dy knowing xi. So basically, yeah, we have our own kappa for all the links between the y1 and x1s, y2 and x2, etc. And the big training sequence and the big sequence of outputs is sampled according to this product distribution. So the product of all the smaller kappas, individual kappas. And obviously, as before, we do not know the input distribution of this framework. So Q is not known. And of course, the kernel is not known. Otherwise, why bother? So yeah, Q and kappa are not known. And yeah, once again, we can write the true loss of a certain hypothesis. And we can denote it as follows: L of Q kappa for a certain H. So it doesn't change. It's still the probability of having differences between the hypothesis applied to X and the actual output Y. But what changes is this QK here, or Q kappa, sorry. And this obviously comes from Q as in X is distributed according to Q. And kappa is the conditional probability distribution. But this notation of Q kappa only states that we have a probability distribution of xy denoted as depending from Q and depending from kappa. And to simplify this meaning, we actually use something that is used in measure theory, which is called a mixture. And basically, this is a mixture of kappa with respect to Q. So basically, we can consider here that this measure is done regarding the mixture Q kappa. So yeah, this is not a product per se, but it's just a notation. So don't be afraid when you see Q kappa. Okay. And once again, we can do as we did before. So we can consider that the training sequence that we saw just here can be seen as a big S of n with inputs, outputs, x1, y1 until xn, yn, big x1 and big xn, etc. While considering that these big x1 to xn are IID random variables with distribution Q and a random vector of random variables y1 to yn with the conditional distribution, as we've said before, which is this probability according to the product distribution of the individual kappas. So the kappas of dyi knowing xi. So yeah, this can be another way of seeing the training sequence that we had before S of n. And this is denoted as we did as well with the Q and F. This can be denoted this way. Big S of n is distributed according to the mixture Q kappa to the power n. So it's the notation to talk about this type of distribution. Okay, and we can now also write the true loss this way. So as we've seen, you take the sequence, you apply the algorithm to it, you have an hypothesis, and the true loss regarding Q kappa of this hypothesis is nothing else than the probability of having differences between the hypothesis applied to the input and differencing that with the output. Of course, knowing a certain training sequence. So yeah, and once again, X distributed according to Q, probability distribution equal to kappa. And here, where you have XY independent of your sequence here. So yeah, this is another way of expressing the true loss as we did before. Once again, it's not much different, the construction of what we are going through here. Yeah, one more notation here, one more fact that is interesting. We consider that for any output y that we have, that we observe, the singleton of y is measurable. So basically, we can say that every output, we're saying that every output that we observe, we can compute the probability of it, so of observing it. So yeah, we consider that every output that we observe is measurable. Otherwise, it will be a bit more difficult to work on it. And just to do a throwback on the first case and to show you that this is nothing more than an extension of the first case, if this kernel, so yeah, don't worry if you didn't get the principle of this kernel, as if you take this kernel as the indicator of y equal to f of x for some measurable function, then you come back to the previous case that we had before, with f a target function. So yeah, this is just an extension of this case, and the previous case is just a particular of this one where kappa is equal to an indicator of y equal to f of x. So that's it for this definition. So we can now move on to the next part. And actually, now may be the best time to take a step back and try to figure out what we actually want from this noisy learning framework. Because you see, it was obvious when we were in the basic learning framework, we had inputs, we had a black box, and we had some outputs. And we were trying to figure out, as best as possible, the inner workings of the black box, namely some function f that we were trying to approximate as best as possible via some hypothesis. That's what we were trying to do before. But what are we trying to do now? I mean, we have this kernel kappa. We're not trying to figure out kappa, right? Kappa is just some indication of the channel, if you wish, between inputs and outputs. So you're not trying to figure out the channel, right? So what are we trying to do, really? So once again, we are trying to get the best hypothesis possible, which is basically the hypothesis describing as best as possible the link between inputs and outputs. And here, the way we can gauge how good of a job we've done is by maximizing the probability of observing some output given some input. So bear with me here because this is really important. I mean, if you've understood it so far, that's good. But if you didn't understand what we're trying to do in this part, bear with me. The only hope that we have in the noisy learning framework is to maximize the probability of observing some output given some input. Because this is real life situations, because this is subject to uncertainty, this kappa represents uncertainty. So the only hope that we have is for us to maximize the probability of having some output given some input. And so basically, yeah, once you apply your hypothesis, you can only hope to maximize the probability of having some output. And your goal is to maximize the likelihood of that observation. So let's describe mathematically what we just said here. So basically, this is done via some mapping phi, which links x to the supremum for all the y's of this kernel, kappa of y knowing x. So you get this mapping and you make sure it's measurable. And you create this mapping h tilde, which basically links x to some output y, which belongs to argmax of your kappa. Basically, you want here this h tilde to give you the outputs that maximize the value of your kernel. This is all you can hope for in this framework. You cannot hope for more or more certainty. You can only hope for a maximal likelihood of observation. And so, yeah, you define this function. So x associated to y in argmax of the kernel, with obviously some arbitrary tie-breaking rule in the case where you have equality. And you make sure that this mapping is well defined and measurable. We will name this mapping in a second, but obviously you've read the title of the slide. But yeah, given that, then you can know for sure that for any hypothesis H within your space M, you have a lower bound on your true loss of any hypothesis, which is the true loss of your H tilde. And this true loss is defined by this quantity over here. So yeah, you won't have a true loss lower than this one. So you may say, great, that's a great result. I mean, if I want a lower bound, then I have it. Well, yeah, but you neither have phi and nor q. So yeah, reality is sometimes disappointing. But yeah, basically, you still have mathematically access, at least, to the true loss of this H tilde. And we will stop calling it H tilde. Such a mapping is actually called the base optimal hypothesis, because this is some optimal hypothesis since it maximizes the kernel. And it has, therefore, the lowest possible achievable true loss. And yeah, since this is the goal, it's interesting to see that any loss of any hypothesis will be necessarily bigger than the loss of this base optimal hypothesis. So you can define this quantity, which is none other than the excess loss of some hypothesis. Basically, you take the loss of your hypothesis minus the loss of the optimal hypothesis. So yeah, if your hypothesis is optimal, this will be 0, and otherwise you will have some excess loss that you can refer to. Okay, so yeah, if you followed me on this principle of maximizing the probability of observing some outputs given some inputs once you apply the hypothesis, if you understood that, you're good to understand what we are doing in this part of the noisy learning framework. So yeah, that's it for this definition here. And a quick example just here. Basically setting us in a binary case where y is none other than 0, 1. So you let H tilde be the base optimal hypothesis with x distributed according to Q. And you get eta, which is your kernel, basically for an observation of a 1 knowing some input x. And in that case, you have that the true loss of this hypothesis is the expectation of this quantity, which is upper bounded by 1/2. And this is actually a measure of the uncertainty, if you will, because you take the minimum of eta and 1 minus eta, and it gives you a measure of uncertainty. In the case where you're the most uncertain, this is 1/2, and in the case where you're completely certain, this is 0. And over here, for any hypothesis, you can compute the excess loss, which is equal to this quantity, with this indicator function here, making sure, of course, that your hypothesis is not optimal. Otherwise, there's no point in computing an excess loss. And fun fact here, you can observe that this excess loss here actually weighs the disagreement between H and H tilde by judging how far eta is from 1/2 because of this quantity here. So once again, there's an idea of measuring uncertainty. So very interesting results that you may refer to if you need. Okay, and one last thing on this noisy learning framework. It's the definition of PAC-learnability, something that we saw before in the previous framework. And you'll be happy to know that it's verbatim the same idea. Basically, once again, we take some hypothesis class. You remember that this means that we reduce the scope of where we search for the solution of the problem. So yeah, some hypothesis class H belonging to M, which is called Agnostic PAC-learnable. If you have some learner and a function that we call the sample complexity, basically telling you the number of samples necessary to have some condition on performance, that's what we saw before, such that for every value of epsilon and every value of delta that you wish within 0, 1, for every distribution Q over X, and for every probability kernel, now we're not talking about target functions, of course, for every probability kernel kappa from X to Y, as long as your training sequence is well distributed according to the mixture Q kappa, and most important, once again, that you have a number of samples sufficiently big, bigger than the sample complexity for your given epsilon and delta, then you have a guarantee of performance of your algorithm, once again, namely that the probability of the true loss of your hypothesis being smaller than some value will be bigger than 1 minus delta. And slight difference here from the previous case. As you can see, you can actually write your true loss as being smaller than the infimum for the values of H, for all the hypotheses, of the true loss within your class H. So basically, we're just saying that this could be 0, this could be not 0, but regardless, we won't have an hypothesis with a lower loss than the one for which we have the infimum within the class. It's just saying that we know that there is some infimum within the class H for the value of the loss. So that's an information that we can have here. And so this infimum to which we had epsilon as before, then the loss of the hypothesis, which is the outcome of the learner, will be smaller than the smallest loss plus some epsilon, with a guarantee of that happening bigger than 1 minus delta. So yeah, once again, a very strong result which guarantees some performance on your algorithm. So this is agnostic PAC-learnability in that a noisy learning framework. And you may know that an agnostic PAC-learnable class is also PAC-learnable. So there is an implication. Agnostic PAC-learnability implies PAC-learnability. Okay, I hope that was clear. So yeah, now that we've talked about this noisy learning framework, you are completely equipped for the generalization of learnability of the framework, basically, in the next part. So let's move on to the general learning framework. And the goal in this part is actually to gain in abstraction compared to the previous cases that we had of the basic and noisy learning framework. But actually, we're going to start in the same state of mind that we had in the noisy learning framework. And you will see a few generalizations that we will make to gain in abstraction. So let's start here. We consider a noisy learning framework where the product set of the input set and the output set, X and Y, is actually written as Z. So you had the couples of the observations that you had of input, output, and you now consider that they don't belong to an input space and an output space, but they belong to a product set, which is Z. And once again, another thing, the mixture that we had between kappa and Q is now written as a capital Q. So now we entangle the notions of probability kernel and input distribution as this big Q, which will be the distribution. And so your couples of X and Y's are distributed according to this big Q. And once again, there is a new expression to your true loss given these new terms. You can write your loss no longer as depending of Q kappa, but of this big Q. So LQ of H is once again the probability of having differences between your hypothesis applied to X and Y. And in practice, you now know that this is the expectation of having an indicator function which gives you the differences between H of X and Y. Basically, you have a 1 if when you apply H to X, you don't get Y, and a 0 if you actually are spot on and you get Y. But this indicator function can actually be generalized as some particular case, some particular way of gauging the loss of your hypothesis. And this is basically saying that this can be written as the expectation of some function L, which depends on your hypothesis and on your observations X and Y. And so basically, this is some function. In that case here, it is the indicator function that H of X is different from Y, and we call it the 0, 1 loss function. But keep in mind that this is just some loss function, which can be different from this very simple 0, 1 loss function. It can be, I don't know, the L1 loss function, L2, SVM, whatever loss function that you wish to have. And basically, this is our way into the definition of this general learning framework. Okay, so let's begin this definition. So basically, we have now two measurable spaces. So as I told you, this is the set Z, which contains the couples of the observations, and its sigma algebra to have a measurable space. And M, the set M, which contains the hypothesis, endowed with its sigma algebra once again. And Z will be called the data space because it contains the observations, X and Y's. And M contains the hypothesis, so it's well named, the hypothesis space. And now that we've defined this new set Z, there's another way that we can redefine the learner that encompasses this generality. Basically, you just write A as the union of elements within this set Z. You take n elements within this set Z, which shows you the size of your sample. And this algorithm returns you an element, an hypothesis within M. So that's your mapping A. And you recognize as well the training sequence that we had before, which is S of n, as elements from 1 to n. But we no longer here have the observation couples of x1, y1, x2, y2, etc. to xn, yn, but simply elements s1 to sn, which belong to z of n. This is only a way to generalize and simplify the notations to gain, once again, in abstraction. So yeah, you have this training sequence in Z of n. Okay, and this remains unchanged. The output of this algorithm remains some hypothesis H, which belongs to the set M. Okay, and not much change in the objective, as we always want to minimize the loss of the hypothesis that we give as an output of this learner. But we now can say that we are working in a space where we have a probability measure which is big Q over some set Z, representing the data distribution. And obviously, we don't have access to this big Q, which used to represent the small q in the basic learning framework and the q kappa in the noisy learning framework. So this is now the big unknown of this framework, which is the input distribution of the data distribution now, big Q. And in this case, there is some function L, as we said before. This is a loss function. And this function is assumed to be known to the learner, which is something that the learner can, you as a programmer of the learner can choose. So yeah, you choose some way of gauging the loss of your algorithm. So you know this loss function, you don't know this probability measure Q. And you can now write this true loss for any hypothesis as this very simple formula, which is simply the expectation of your loss function, which depends on your hypothesis, of course, and a random variable z distributed according to Q. So yeah, simpler expression and more general one for the true loss of your hypothesis. And we find once again the definition of the empirical loss, which is something that we can access, which only depends on data that we have. This loss function, which was chosen, and your training sequence, of course. So you compute the loss for every value of your training sequence, and you take the average of it for the whole length of the sequence, and it gives you the empirical loss of your hypothesis. So no difference in the way that we compute it, except that now we talk about a loss function here. Okay, and as we did before, we created this big S of n to talk about the training sequence, but we still talk about the same sequence. Only that now we consider that these big S over 1 until big Sn are IID random variables with common distribution big Q. And once again, this is denoted big S of n distributed according to big Q to the power n. And so this gives you a brand new definition, which will be the more general definition that we will have for the true loss of an hypothesis. Once again, this is your training sequence. You apply to it the algorithm. This is an hypothesis. And the true loss, according to Q, of your hypothesis is the expectation of some loss function, which depends on your hypothesis and on some random variable z distributed according to Q and independent of big S of n, which we know, obviously, which is why this is knowing big S of n. So this is the more general definition of the true loss. Okay, and once again, we can define a smaller class, as we've seen, in which we know, which is included within M, which can reduce the scope of where we are searching for the hypothesis. Once again, this is the hypothesis class. And to finish on this, we can say that the data space has a product form if we have Z as a product of X and Y for some measurable spaces, X endowed with its sigma algebra, Y endowed with its sigma algebra, and with M, the set of measurable functions from X to Y. So this is only what I was telling you orally before. Just the fact that this is a way of considering, of encompassing what we had before as a product between X and Y. Okay, so that's it for this definition, and we can now move on to the generalization of the agnostic PAC-learnability. And you will see that there is not much change compared to the noisy learning framework. It's only that we introduce this notion of the distribution of big Q, which changes compared to the mixture Q kappa. But you basically see this is the same as the previous slide we saw on agnostic PAC-learnability. So some hypothesis class H is called agnostic PAC-learnable if there exists a learner A, once again here the union of elements within Z to the power n, giving you a result in M, and some sample complexity NH, now you know how it works, such that for every value of epsilon, every value of delta that you wish within 0, 1, and for every distribution Q over your set Z, as long as your training sequence is well distributed according to Q to the power n, and that you take a number of samples sufficiently big, bigger than some sample complexity NH, depending on your epsilon and your delta, you have a guarantee of performance for the third time in this presentation for your hypothesis, which means that you can actually know that the probability of having a loss smaller than some value can be bigger than 1 minus delta. And once again, the probability of having your loss smaller than a value here is depending on the smallest possible achievable loss within your hypothesis class H. So once again, this depends on the infimum of all the losses within your class H, because you won't be able to have a loss lower than the infimum, obviously. So that's an information that you have. Once again, this is the same idea as we had in the noisy framework. It's just that you have this loss smaller than some infimum plus epsilon with probability bigger than 1 minus delta. So you have a guarantee of performance of your learner. Okay, great. So we can now move on. Hopefully this is all clear. There's not much that has changed. We only made some abstractions on this space Z, and the distribution is now written as a big Q. And the final item that we need to adapt from the previous framework is the empirical loss minimization algorithm, the ELM. And nothing has changed really here. The ELM with respect to H remains a learner, denoted ELM-H. The only change is that the sequence is now in Z of n, your set of couples. And this is still the algorithm which provides an hypothesis which minimizes the empirical loss, big L. Whenever, of course, argmin is not empty, you have this algorithm well defined. And in that case, the mapping from Z of n now to M, which associates one sequence to its hypothesis via ELM of H, is measurable. Okay, and a few results in that case given by this lemma, which tell you that this minimum is actually achievable in two cases. The first one is the hypothesis class H being a finite set. So when you have a finite hypothesis class, you know that you can achieve for sure this minimization of the empirical loss. And the other case is when your loss function actually takes a finite range of values. For example, we saw before a 0, 1 loss function. So there are two possible values for your loss function, 0 and 1. So this is a finite range. So whenever your loss function has a finite range of values it can take, you know that you can achieve your minimum and minimize your empirical loss. Okay, and maybe a quick illustration of what we saw in a very simple example. Why am I saying that this is simple? You'll see in a second, because we're talking about linear fitting as a machine learning problem. And why is it simple? Because when you talk about linear fitting, you actually consider an input space, which is R, an output space, which is also R, and your hypothesis is just a measurable function from R to R, and you target an affine function f. And basically, this is why it's simpler. It's because you have a big insight on what you wish to find as the shape of your hypothesis, because you know that you're looking for some function which resembles this, basically ax plus b, and we denote it here beta 0 plus beta 1 x. So yeah, you know that the function you're looking for is in this class HA. So this simplifies the discussions. And basically, you take some loss function. Here we decided to take a squared error function, which basically takes y minus h applied to your input x. And this is the loss function that you will use to compute the empirical loss of some hypothesis. So yeah, basically you run your algorithm, you try to estimate the behavior of some black box, which you know is an affine function, and it provides you an hypothesis of this shape, beta 0 plus beta 1 x, with respect to the training sequence that you fed it. And now you can compute this empirical loss as basically the average for all the individual losses for all the samples that you have. You compute the loss and you take the average of it over the amount of samples. And basically, when you apply this L of H and apply to every couple xi, yi, it gives you this formula here. Since h of x, this was y minus h of x, and h of xi gives you a minus beta 0 minus beta 1 xi, everything squared here, and you take the average of this and you get your empirical loss for your hypothesis. And in that case, you have that ELM of HA. This was your class, which was reducing the scope of the type of function you were looking for, leads to the least square fitting. So yeah, this is the way you would do it if you were doing a learning problem in order to solve linear fitting, in order to have least squares fitting. So yeah, in that case, you see that it's quite easy since this scope is very narrow. In real life, you don't necessarily always know which type of function you're supposed to look for, what your actual solution looks like. You don't necessarily have that knowledge. But in that case where you want to do linear fitting, you can reduce your scope to this class HA. Okay, another concept that we can introduce is the concept of epsilon representativity. But before that, let's talk to see where this comes from. Let's talk about a comparison between the hypothesis produced via some ELM and the optimal hypothesis, because there is something that we can say to compare both losses. So let's take a sequence, Sn in Z of n, and some hypothesis H hat produced by ELM of H from that sequence. And in that case, there's actually a way to gauge the difference and to upper bound the difference between the true loss of that ELM hypothesis and the optimal hypothesis that you could have within your hypothesis class, which is this, the true loss of some hypothesis, the infimum of the true losses on your hypothesis class H. And this difference can be upper bounded by some quantity, which is this, 2 times the supremum of this difference. Basically, if we look at it for a second, this is actually giving you a comparison between the empirical loss and the actual true loss for all the hypotheses within your class. And you are taking here, in order to upper bound this quantity, you are taking here the supremum for all the hypotheses within your hypothesis class of this difference. Basically, you find the hypothesis which has the biggest discrepancy between the empirical loss and the true loss. And you take this difference as, well, you take twice this difference as the upper bound of this comparison between true losses. Okay, if you didn't get everything I meant here, just consider this quantity, which is the upper bound, the supremum, sorry, of these comparisons between empirical losses and true losses within your hypothesis class H. This supremum here is what we will use to define epsilon representativity. So what do we mean by that? We say that a training sequence Sn in Z of n is epsilon representative if this quantity, this supremum between empirical loss and true loss, can be upper bounded by some value epsilon. Basically, that your sequence is good enough so that there is only a reduced gap between the empirical loss and the true loss for all the hypotheses within your class. The worst case is still a difference smaller than some epsilon. So in that case, if you can verify this, you say that your training sequence is epsilon representative. And an obvious corollary that derives directly from this first formula here, which you will understand in a second, basically telling you that you take a sequence and H hat as a result of ELM of that sequence. You can say that some sequence is epsilon divided by 2 representative, and this implies that the true loss of your hypothesis is smaller than the optimal loss plus some value epsilon, some small value epsilon. Basically, once again, this shows that your sequence is good enough. The smaller this value is, the better is your sequence, because you minimize this loss and it gets closer to this optimal loss. So that's the point of doing this. It's to show you that there is a way to upper bound, or to at least have an idea of where your true loss for some ELM is located by comparison with some optimal hypothesis. And we will use that immediately. So this quantity that we use for epsilon representativity is used to define another concept, which is the uniform convergence property. And we say that some hypothesis class has uniform convergence property if there exists some uniform convergence sample complexity, but this is still the same idea that we saw before. Some amount of samples that we need to take in order to have some results. So it's still the same idea. We will need to have, spoiler, n bigger than some nh for some epsilon, some delta. Okay, so you have uniform convergence if there exists some sample complexity that verifies for any value of epsilon and any value of delta within 0, 1 for every data distribution Q over Z, and as long as you have a training sequence well distributed according to Q to the power n, and obviously a number of samples sufficiently big, you can guarantee that this quantity that we saw, this supremum, is smaller than some epsilon, that your training sequence is epsilon representative, with a probability greater than 1 minus delta. And just a precision here, you can see that we're not using the actual probability, we're using this P star. And don't worry about it too much, but basically this is just a precaution, because this supremum that we are taking over this class H is not necessarily measurable. So we have an issue of measurability here, which implies that we can't always take the probability for that supremum. So this is a technicality, but in practice, we can't use the probability. So we define this P star, which is the inner probability defined by this quantity. This is basically a safety measure to avoid any mathematician to get angry at us. So yeah, basically that's just a precaution to avoid the case in which this supremum is not measurable, but you can consider it as just taking the probability in the regular case. Okay, and this this implies actually that you have a link. As you can see, this formula very much looks like what we had in order to define PAC-learnability. And so in that case, you can see that there is a link between uniform convergence and PAC-learnability. This is intuitive, but we'll see why in a second. You can have uniform convergence and a well-defined learner. Then in that case, your hypothesis class is also agnostic PAC-learnable using that same learner with the following sample complexity, nh for some epsilon and delta, equal to nh for uniform convergence for epsilon divided by 2 and the same delta. Why do we have that? Well, maybe you figured it out already, but if you recall what we saw for agnostic PAC-learnability, it was this. The true loss of our hypothesis was supposed to be smaller than the optimal loss plus epsilon, with a probability greater than 1 minus delta. But what we wanted was the true loss of our hypothesis smaller than the optimal loss plus epsilon. And actually, we do have a characterization of this right here in the corollary. If the sequence is epsilon divided by 2 representative, then we have exactly that. The true loss of the hypothesis is smaller than the optimal loss plus some quantity epsilon. So we can have the same result here that we had for agnostic PAC-learnability. We can find a link between uniform convergence and agnostic PAC-learnability as long as we take the sample complexity for epsilon and delta equal to the uniform convergence sample complexity for epsilon divided by 2 and delta. So this is a nice little link that you have between these two concepts that we introduced here. Okay, and for the final results of this presentation, we actually have a very beautiful result, which actually traces back to what we saw in the first part of this presentation in the basic learning framework. when we were talking about finite hypothesis class. So far, we didn't make any assumption regarding the finitude of the hypothesis class H. And we will see that we actually have a result, a performance result, a performance guarantee, in the case where this class is finite. So yeah, we can take a loss function L and a sequence distributed according to q to the power n and some value delta in 0, 1 fixed however we want. Then for any finite hypothesis class H, we have this performance guarantee basically telling you that the difference, once again, the difference between the empirical loss and the true loss for the worst case, basically the case where this gap between empirical loss and true loss is the biggest within your hypothesis class H, can still be upper bounded by this quantity with a probability greater than 1 minus delta. Couple things here. Well, this quantity, which I'm not going to explicitly say, you see it as well as I can see it, shockingly resembles what we saw in the very first part when we were having a log of cardinality of h divided by epsilon over divided by delta over epsilon. Well, this is a more advanced version, obviously, because we're not talking about the same quantity here. But it's still the same idea that we have and the same type of quantity that we are up-bounding our performance guarantee with. And just a quick precision as well, you can see that here we are taking the actual probability. Since we have an hypothesis class that is finite, we can now always take that supremum. So there's no problem, there's no angry mathematician. So, okay, and yeah, maybe to take a step back, this is a very strong and beautiful result. Once again, we were doing empirical losses, we were computing empirical losses because there was no way for us to access actual true losses. So yeah, we were talking about these true losses everywhere during this presentation, but you know, when you're like actually programming stuff, there's no way for you to compute this. So you may be wondering, well, that's interesting mathematically, but what about me? You know, in reality, I can compute that. Well, this is very, very strong because it tells you that if you manage to have some finite hypothesis class, well, you know that your computation of the empirical loss is good enough, basically, that you won't have too much of a gap between this empirical loss that you're able to compute and the true loss of your hypothesis that you will never be able to compute firsthand. This difference remains, in the worst case, smaller than some quantity that you can play with. Actually, this depends on n. So if you want it to be even smaller, you can just take a greater amount of samples to lower this. So yeah, this is once again really, really strong because this is variables that you can actually play on, that you actually have a hand to control. So that's really nice, and you're able to once again have this guarantee of performance telling you that taking the empirical loss is good enough within some margin with a guarantee greater than 1 minus delta. So yeah, very strong result that you have in this case. And maybe a quick corollary to end things. Basically telling you that once again, you take a loss function and you assume a finite hypothesis class. The reverse, basically H as uniform convergence property with uniform convergence sample complexity equal to this logarithm. Once again, looking a bit like what we saw in the beginning, but not exactly the same. And once again, if your algorithm is well defined, then you have agnostic PAC-learnability, as we saw before, with sample complexity for epsilon and delta equal to the agnostic, the uniform convergence sample complexity for epsilon divided by 2 and delta. So yeah, this is applying what we saw before. So yeah, beautiful results in this finite hypothesis class case. Well, that's it. Thank you very much for your attention. This is a bibliography with the references that were used to make this presentation. Don't hesitate to give your opinion in the comments. We will read them and answer you to the best of our abilities. And don't hesitate to check out these sources if you're interested. And don't hesitate to check out another video on this channel. It's very interesting. It's very cool. Yeah, and I'll see you soon. Thank you very much. Bye-bye.